Okay, friends, get ready for this super short, super abbreviated version of Descartes' Rule of Signs, Section 5 from Chapter 11 of your book, and the last one we're going to do from this chapter. So, Descartes' Rule of Signs is sort of a shortcut. It's never necessary, but sometimes it helps us out. So technically, you don't actually have to use this to solve any of the problems we're trying to solve, but sometimes it can be a big help. So, for example, because that's the best way to explain this than to try to give you a rule, whenever we have any kind of little polynomial, no matter what the sign, what we do is count the number of times the sign changes. In this case, if we skip a power, like if we don't have here an x to the fourth, we don't have an x to the third, it doesn't matter because those terms would have a 0 as a coefficient, 0x to the fourth, 0x to the third, and that means they don't have a sign either, and we're just looking at signs right now. So this first term has a positive, the second one has a negative, the third has a positive, and this fourth one has a positive. So we read this from left to right and we count how many times the sign changes. So positive to negative, that's one change. Negative to positive, that's two changes. Positive to positive, not a change, it stayed positive. So there are either, now this part is a little tricky, 2 or 0 positive rational roots. Because there were two sign changes, there are at most 2 positive real roots. But there could also be 0 positive real roots, and that's how it always works in pairs. Why in pairs? Because irrational numbers and because complex numbers come in pairs. You'll remember that we talked about if 2i is a root, negative 2i is a root. If 2 plus the square root of 7 is a root, 2 minus the square root of 7 is a root. Those always come in pairs. So that means our positive rational roots will always go down by 2's. So if we had found, for example, if we had found 5 sign changes, that would mean there are either 5 or 3 or 1 positive real rational roots. If there had been 10 sign changes, that's a lot, and it would have been a huge polynomial, but if there had been 10 sign changes, there would be 10 or 8 or 6 or 4 or 2 or 0 sign changes. So is this even useful at all? Well, that certainly doesn't feel very useful, but let's move on to find the negative sign changes, and this part is a tiny bit tricky. What you do is kind of mentally, you don't have to actually physically write it in the way I did here, but you mentally substitute in a -1 and ask, what would the sign be if I plugged a -1 in? You can physically do it if you want to, but you don't actually have to do the work. If I put a -1 here, -1 to the fifth is a negative number, so that 2 would be a -2 and the whole sign would be negative. If I put a -1 in here, -1 to the second would be positive, times the -5 means the sign stays negative. If we put a -1 in here, 3 times the -1 gives me a negative. Remember, we're not worried about the actual number, just the sign. And because there's nothing to plug in here at the constant, we just keep the sign it already had. So you mentally plug in, and what happens is every time you have an odd power, that means we end up with a negative and it changes the sign. So that 2 went from positive to negative. Whenever we have an even power, that causes it to be positive, so it does not change the sign and it stays the same. So that -5 remained negative. Again, we have an odd power here because it's 3x to the first. There's that invisible 1. 3x to the first, that's an odd power, which causes the sign to change. So you're plugging in a -1, but you really just want to know what's going to happen to the sign. And when we do that, we get negative, 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 positive. So there's only same, one sign change when we go from negative to positive. Because there's only one sign change, we can't count down any lower. because we would have to take away 2, and it doesn't have negative roots. It doesn't work that way. We can't have less than 0 roots. So because we have a 1, that means there is 1 negative rational root. Does that help us? A tiny bit. What it tells us is there might not be any positive rational roots, but there is definitely 1 negative rational root. So when we make our list like we did in section 4 and we write all of our possible roots, in this case, you can see that there's, let's see, positive to negative. So there's 1, 2, 3 sign changes. That means there's either 3 or 1 positive rational roots. That means we can be sure there is one that's positive. So when we test all of our roots, we'll test all of the positive ones first because we know there definitely is one. When you get an even amount like 2 and you get 2 or 0 the way we did over here, then that means there might not be any. So you don't want to check those first. For this problem, you'd want to check your negative numbers first. So when you make your list, you'd try all the negatives ones first because we know there is one. We're not sure whether or not there is one here. In our final answers, on this problem, it said there were either 3 or 1 positive sign changes. Let's do the negatives. I'm going to mentally plug in a -1. A -1 to the 4th is a +1, so this stays positive. +1 times +3 is still positive. -1 to the 3rd is a -1 times -11 would turn this positive. Again, you can see that odd power changes signs. Even powers stay the same. If I put a -1 in here, it would be -1 times 10, so that would make that sign negative, and there's nothing to plug in here, so we keep it the same. This tells me with only one sign change that there's 1 negative. Again, I can't count down from there. So there's either 3 or 1 positive and 1 negative. If you remember our answers from our last lesson, we ended up with 1 positive, 1 negative, just the way the rule predicted. And then we had 2 that were irrational and weren't explained by that rule at all. So all you have to do on the actual assignment for this problem, for this section, is tell how many possible positive or negative roots. That part's pretty easy. They don't actually make you find them. But if you know this rule, it can save you a little time on some of those longer problems that we did yesterday, because you might be able to eliminate something. If there are no sign changes, it means there are no positive real roots, and that means you don't have to check any of the positive real roots. So, once again, try the problem that's listed in the description on your assignment. Give those a try. You can check them in the back. You can ask me questions through whichever method works best for you. And then take that little assessment that's included so that you'll get some feedback. And then we'll start reviewing for this test. And I'm not sure yet what it will look like, but there will be some kind of assessment.